Hey Geometers, welcome back to another lesson with Mr. Forster. Today we are going to be covering solving algebraic equations, which is our third lesson in Unit 1. There is a homework sheet attached to this. There is also a review that will be posted alongside this video. We have our first quiz coming up on Wednesday, September 2nd. So make sure you're working through that review. We'll spend some time in class on Tuesday reviewing together, but your class plan for Wednesday will be to be taking the quiz. Before we begin solving our equations, just a reminder on some of the things that you can do to solve these multi-step equations. The first thing you often want to look for is using that distributive property. The next thing is to look to see if there are any terms that can be combined on each side. Then we can look to see if we can move the variables to just one side of the equation. Look for any addition or subtraction that you can undo. And finally, to isolate the variable completely by itself, look for any multiplication or division that can be undone. For our first example, we start off here with 3x take away 35 is equal to 9x take away 59. So we're showing each step as we go, and we talked about this briefly in our previous lessons about how we're introducing some of the ways that we communicate in geometry, and we're going to revisit algebra to help us with this. The first thing that I've done here is I've subtracted 3x from both sides of this equation, and that leaves us with no more variables on the left and only negative 35 left on the left. On the right side, 9x take away 3x leaves me 6x, and I still have take away 59 here. If I want to isolate those variables, or that variable here, I'm going to add 59 to both sides. That takes care of this subtracting 59 on this right-hand side, leaving me with 24 is equal to 6x. And then finally, to get x by itself, I'm going to divide 6 on both sides, and I get 4 is equal to the value of x. So we have two examples here that I want you to try on your own. We have A and B. I've done formatting on each a little bit different, so in A you can kind of see where each of the steps is going to take place. In B I've done it to where they will appear on the screen, but I want you to pause and give yourself a few minutes to try A, and then we'll walk through it. Right, for A, the first step that you may notice is we have this 8 here that needs to be distributed into this set of parentheses. So 8 will multiply by the 1 as well as that 5x on the inside, leaving us with 8 plus 40x plus 5 is equal to 13 plus 5x. And then from here we can combine the like terms on the left side, combining the 8 and the 5 since they are both constants without a variable, and we get 40x plus 13 equals 13 plus 5x. Next, we're going to subtract 13 from both sides. This gives us that 40x is equal to 5x. And then I can subtract 5x from both sides, leaving 35x equals 0. And then here, these little bars here, these fraction bars, mean I'm dividing, so 35x divided by 35 is equal to 0 divided by 35, which leaves me with x equals 0. Moving on to part B, again I want you to pause here and try on your own. I have another instance where I notice that I need to distribute into these parentheses or brackets, so negative 1 here, this not written, but there would be like having a negative 1 here. So this negative needs to be distributed in. This negative 6 also gets distributed in. On the left, I have negative 1, and then this negative goes to the 7x, so I get minus 7x. And then negative 6 multiplied by negative 7 gives me plus 42. And negative 6 multiplied by negative x gives me plus 6x, and this is all still equal to 36. Again, I'm looking for where I can combine like terms next time. So my constants are negative 1 and positive 42. My variable is negative 7x and positive 6x. So the blue combines to make a total of 41. 42 take away 1 is 41. And then if I have negative 7x and plus 6x, I get negative x, still equal to 36. Next, I'm going to subtract 41 from both sides, which leaves me with negative x on the left and negative 5 on the right. And then again, you see the fraction bar here, I'm dividing these. So negative x divided by negative 1 is equal to -5 divided by -1 using my division property. And I'm left over with x equals 5. Transitioning into an introduction into proofs and using some logical statements like we talked about with our which one doesn't belong in last class, we're going to be providing some different ways that we can provide evidence or reason when we do these algebraic operations. So a lot of times we're going to use these properties, and these properties are going to be our justification or our reasoning statement for these, whereas our argument is whatever we're performing within the math. So your normal task when you do these is you're writing out all of the arguments as you work through these problems. Now we're going to also incorporate the reasons that we can do these using some of these mathematical statements and properties that we have. So the first one that we have is our addition property of equality. And it says that if we have two values that are equal, a and b are representing values, then if I add the same thing to each value, then those new values should still be equal. So if you add to one side, and you add to the same value to the other side, then you end up with the same value on both sides. So to keep this relationship equal, add the same thing to both sides. Similarly with subtraction, and the property of equality that goes with that, if I have two values that are the same, and I subtract the same quantity from both sides, then they will stay equal. One way to think of this is in order for them to stay equal, I have to subtract the same thing from both sides. Otherwise, this idea of equality goes away. The multiplication property of equality, again, very similar. If I have two values that are equal, then I can multiply them by the same value on both sides, and they stay equal. Division has one slight difference, and that's that the value that I'm dividing on either side, the c value, can't be 0. It's one of our few golden rules in mathematics, thou shalt not divide by 0. Distributive property, we've seen this a handful of times in our previous examples. If I have a quantity that is multiplying the sum, that is two things being added together, then whatever that value on the outside is, it's going to apply to both of those values. So I get a and b and their product here, and a also with c and their product here. Combining like terms, this is one where I'm looking at all the things on the same side of an equation. So you'll notice that the things that are underlined are on the same side of that equal sign or that equality relationship. And so on the left, if I have 3x and 5x together, they can combine to make 8x. And over here on the right, if I have 4x and -5x, they combine to make -x. Moving on to our first proof, a little note here. We're starting with this 2 times x minus 7 plus x equals 1. And then when you're doing a proof, you typically want to write down the property on the line after you apply that property. So a question you might have is, well, where do I start with this idea of a proof? And where we start is we're going to write out our problem, the thing that we're working on. In this case, it's our algebra equation. And then more often than not, you're going to say given, because this is the problem that was given to you. So you already know this information. You don't have to prove that that information exists. This was given to you. So we use this phrase given quite a bit. You can kind of see I've outlined what the next step is going to be. I'm going to be distributing this 2 into that x minus 7. And so I'm going to get this 2x minus 14, and then the plus x equals 1. That hasn't changed yet. And I'm just naming what I've done in that second column on the right, which is I've applied this distributive property. Now, you can kind of see I've already outlined what I'm going to do next, and you can do this in your work as well. I have a 2x here and an x here on this left side of my equation. So I'm going to combine those things. And so I can already kind of outline what the work that I'm doing is in one step. And then when I actually show that that's happened, that's where my reason's going to come in. What I've done is I've combined like terms. So I'm actually outlining what I'm going to do next in one step. And then once I've done it, that's when I name my reason or my justification, because I've already taken that claim or I've already made that statement. Moving on, we have subtracting 14 here. So what I want to do is add 14 to both sides. And that's going to leave me with what's in black here, the 3x minus 15. And what I've done is I've added 14 to each side. And I can do that because if I add the same thing to both sides, they stay equal. So this is called the addition property of equality, or add prop of equals for short. Mathematicians really like to be effectively lazy. So if you can shorten things and still communicate your point, then that's fantastic. And then finally, in red here, again, these fraction bars that are taking place, which are not just the place that fractions go to hang out after work. You're welcome. That's a math joke / dad joke. We're going to divide by 3 on both sides, and we get x equals 5. And since I'm applying division to both sides, then we call that the division property of equality. Moving on to another example, we're starting off with 6x plus 17 equals 9x plus 2. I'll go through this a little bit quicker this time. Again, since you're given this problem, we're going to write out, this is our given statement, so this is what we're told. So the reason for that is given. Outlining what I'm going to do next, it looks like what I want to do next is to isolate the variable onto one side, so I'm subtracting 6x from both sides. When I've done that, this part in black here, the 17 equals 9x plus 2 is what's left over. And what I did to get there was use that subtraction property of equality. I'm going to apply subtracting again here. I'm going to subtract by 2 on either side to get rid of this constant on the right-hand side. And I'm left again with what's in the black type here, which is 15 equals 9x. And I apply the subtraction property of equality a second time. And you can do that. You can do the same reasoning statement for more than one argument that you've made. Here on number 3, my outlining of what I'm going to do next, these are now dividing this 9. And so I'm going to end up with 9 divided by 9 gives me 1, so just x on this side. 15 ninths simplifies down to 5 thirds. So 15 and 9 are each divisible by 3, so I get 5 over 3. And what I did to get there was divided by 9, so that's the division property of equality. We don't have to state anything about when we simplify our terms. You never have to provide that as a reason. Moving on to our final example here. Again, we're going to start off by restating our problem and stating that this was given to us. We do have some distributive property that we can apply. So we're going to apply this negative to the 5a here, and as well as this positive 27, which is now negative 5a minus 27. And you can see I've outlined what I'm going to do next. The red, these are terms that have a in them, and then the blue are terms that do not have a variable in them. So we're going to combine our like terms. Before we do that, we're going to state what we did to get here, which is our distributive property. And then we're going to combine those like terms. So 4a minus 5a is negative a, or negative 1a. Negative 54 and negative 27 combine to make negative 81. And again, what we've done here is we've combined our like terms. Next, what I'm going to do is in order to get our variables isolated to one side, I'm getting rid of this subtracting 2a by adding 2a. And then I'm going to do the same thing to this side. That leaves me with a on the left. And what I've done to do that is I've added a value, the same value to both sides. So I've used the addition property of equality. And then finally, again, I want to get this a by itself. So I'm going to add 81 to get rid of this negative 81. Do it to both sides of the equation. I'm left with a is equal to the value of 104. And again, another example of where I've used the same property twice in a row. Since I added from here to get to number 4, I use that as my reasoning. And I added here in box 4 to get to box 5. And so my reasoning for how I got to box 5 is that addition property of equality. Here I have a few extension equations. You don't have to write a proof for these, but these are good refreshers on working with things that are what are known as rational values. We have these ratios or fractions built in, and then this one is using absolute value. And so a little hint here, there will be 2 solutions to this. So these are optional to kind of push your algebraic understanding and just keep practicing. Try them if you want, and feel free to email me or ask me in class if you got the right solution. Finally, just a reminder, today was Unit 1, Lesson 3. The homework that you have for this is the homework sheet that's attached to the post in Google Classroom. I will also include the review for Lessons 1 through 3. So this will cover all the way up from our first video lesson all the way up to today. And there will be a quiz that spans across all 3 of those lessons coming up this Wednesday.